This video is for Math 0242-1342. We're going to continue in Chapter 5 and do the second half of that chapter, which is sections 5.3 and 5.4. And we previously did basic and single probabilities, complements, and unions or ORs. So I'm pretty sure 5.3 has to do with intersection, which are ands, and then 5.4 is probably conditional. Or maybe both of these are in 5.3 and 5.4 might be what are called counting techniques. Okay, so probability of A and B. See, this is an and, or what's called an intersection. And it's a very similar concept to whenever you're doing ORs. ORs, you have to know if what you're dealing with is mutually exclusive or not. Because depending if it is or not, you do the formula differently. So there's a probability of A plus probability of B if they're mutually exclusive. That's all you do. Whoops, can't get it in there. Oh. I was trying to write EXCL here, but it ran out of room. Mutually exclusive. So if they're not mutually exclusive, then you do one extra step at the end. So then you get probability of A plus probability of B. Same thing so far. But then when they're not mutually exclusive, you have to subtract A and B, which in those problems, there's not like a formula needed to get it because there is a formula for and problems too that's taught in the next section. This happens if they're not mutually exclusive. Mutually exclusive is just that you can't be both at the same time. And if you can be both at the same time, then there's this extra part that's needed. Ands work very similar. There's a concept about is two events independent or not. Independent is a different concept than mutually exclusive. Independent means that the two events do not affect each other. It has nothing to do with whether they can happen at the same time or not, just do they affect each other or not. So like if you flip a coin and roll a die, the flip of the coin, if you tell me, oh, that coin came up heads, that has no effect on whether I'm going to get a 1, 2, 3, 4, 5, or 6. So that's independent. But if I draw candies out of a bag of M&Ms, let's say, and we'll keep it simple, say there's 10 candies in the bag, and say 3 of them are blue. The probability of getting a blue, the first draw is 3 out of 10 because that's basic or single probability. The probability of a blue M&M is 3 out of 10, 3 out of 3 good ones, 10 total. But if I tell you the first event is drawing a blue and I leave it out of the bag, and then I try to draw another blue one as the second event, well, knowledge of the first event is going to change the chance of my second event. My second event now has a probability of 2 out of 9 because I left one of the blue ones out of the bag. That's what independent is about. So if you're doing and probabilities, and there's some problems where you don't even have to use the formula to get an and. Remember those chart problems that was like all colorful and I was circling rows and columns? If you have a chart given to you, you can get an and just by going to where they meet in the table and you don't need any formula for it. But there's other problems where you need these formulas, and the probability of A and B is taught to junior high kids, and they're just taught, junior high kids when they take their STAR tests, they tell them, oh, if you get an OR probability, add the two things together, and if you get an AND, multiply them together. They're getting the exception cases. They're getting the mutually exclusives and the independent cases that are the easier ones because they can't handle anything harder than that. So it turns out if they're not independent, if one event affects another, then you add one more thing to this, just like you do with the OR problems. It starts off the same, A times B, but then there's this thing called conditional probability, and they put a vertical line for this. So the way this is read is B given A. The vertical line is given, which is what's called conditional probability. If you word it backwards, read it backwards and say, given that A has already happened, now what's the probability of B? Given that I took a blue M&M out of the bag first, now what's the chance of getting another blue one? That's why it switched to 2 out of 9, because that knowledge of the first one affected the second one. So conditional probability has its own formula too, and there's only one version of this. If you put it alphabetically, A given B, its probability of A and B divided by B. Or you can do it the other way too, because it depends what's given to you. You can be given one event or another, or you could arbitrarily change the A's and B's, whatever you're calling them. And so whether you put B and A or A and B and order doesn't matter. So I could write B and A, that's okay, but B and A is the same thing as A and B. But in conditional, order does matter, because you basically divide by the second half. Whatever the second half is, that's what you divide by. So it does matter in that one which one's first, which one's not first. So back to here, they say find the probability of A and B. They tell me A, they tell me B, and then they give me this B given A too. See, that's conditional probability. So if I write the I'm going to use this formula right here, B given A. And we know the probability of this. The probability of B given A is 0.6. So I can put that right in the answer slot, 0.6. B given A. And we know the probability of A is 0.8. That's the denominator. And we're looking for B and A, because B and A is the same thing as A and B. That doesn't really matter. So it's like you have an algebra equation where 0.6 equals something that we just call x in algebra. Something divided by 0.8 has to equal 0.6. So you can solve this algebraically and just multiply both sides by 0.8. And 0.8 times 0.6 is 0.48. So you're kind of solving this indirectly backwards by taking other given information and plugging it into a formula. So sometimes it helps to have these formulas, and I'm going to send you a formula sheet that you get to use during tests. So I got to just remember to do that in one of my morning emails. Okay, now see here it says it's independent. This is the easier case. Now you're back in junior high. Assume A and B are independent, find A and B. That's literally A times B. This would not work in the previous problem, but it works here. 0.4 times 0.7 is 0.28. So that's why you always got to worry about ands and ors. There's always this extra worry about, is it, where did I write it? Here. If you're doing ors, you got to worry about, is it mutually exclusive or not? Because if it is, there's an easier formula to use. You just do a junior high formula, basically. And if they're independent, it's easier too. You just multiply them. But these are rare cases in college level statistics. You don't get these two easy cases very often. So if you get like 3 or 4 ands on a test and you're just doing the easy version on all of them, you're probably going to miss many more than you'd get right. But you will see this on occasion because it is one of the rules. Independent is nice. If I flip a coin and roll a die, I can just multiply the two probabilities together. Okay, a fair coin is tossed 3 times. What is the probability that all 3 tosses are heads? Write your answer as a fraction or a decimal rounded to 4 decimal places. Okay. Another way you can do probability kind of generically is something called a tree diagram. So I'm going to flip a coin. Coins come up heads or tails each time I flip it. So you just branch off like trees. This is the first flip of the coin. Now do it again for the second flip, because if you flip 3 coins, it doesn't matter if you flip the same coin 3 times or if you literally grab 3 different coins and flip them all together, kind of like throw them all up in the air and then look what happens on the ground. So because coin tossing is independent, one flip doesn't affect the other, you can do them separately, one at a time, or all together, and you get the same results. So now do it a third time. Each time you branch off an answer and you get another heads or tails going on. So the number of possibilities doubles every time you flip the coin again. First there's 2 possibilities, then it doubles to 4, then it doubles to 8. And if you do the flipping or the experiment too many times, then tree diagrams become too cumbersome to work with. But if you only do it maybe like 3 or 4 times at the most, or certainly like 1 or 2, then this is an easy way to get answers right. So all you have to do is follow the path to the end of each one. This top heads right here came from this path right here. So one possibility is heads, heads, heads. Another one is heads, heads, tails. Then I can come here and go heads, tails, heads. Heads, tails, tails. There's 4 that start with a head right here, and then it turns out there's 4 that start with a tail. Tail, head, head. Tail, head, tail. Tail, tail, head. Tail, tail, tail. This is what's called the sample space. When you list every possibility, I think we talked about this last time when we just rolled 1 die and there were 6 things in the sample space. So this is the sample space. This is when you list every possibility that can happen in whatever experiment you're doing. The nice thing about having the sample space to look at is you can count how many there are here. There's 1, 2, 3, 4, 5, 6, 7, 8. Any question about flipping 3 coins will automatically have an 8 in the denominator no matter what. That's why I like to list it all out, even though it takes a little while to do that. And they want to know what's the probability all 3 tosses are heads. So now you go back to the sample space. So we want all heads here. There's only 1 of the 8 that has all heads in it. Every other possibility has at least 1 tail in it. And some have multiple tails. There's even one that has all tails in it. So it's literally 1 out of 8. This is single or basic probability where I'm doing good over total. And it's 1 out of 8. It's just a little more complicated to know all the possibilities than the problems in the early part of the chapter, like rolling 1 die. There's just 6 things that can happen, and then it's a little easier to know the sample space. Okay, here's the idea about independent or mutually exclusive or neither. Or I guess you could have both too, but they don't have that as a possibility here. So a student is a freshman and a student is a senior. So if you tell me somebody's a freshman, that's the first event. Can they also be the second event at the exact same time? Can you be a freshman and a senior at the same time? No. So they're not mutually exclusive. Now, if you say I went to a high school or college and I grabbed a random person from a classroom, and I'm telling you that the first event is that that person is a freshman, and now I want to go grab a second person. See, ands are more about doing it more than once, where ors are kind of like, what's in this one time? Can both of them happen at the same time or not? So I grab one person. Here's a freshman. Look, I got this freshman with me. Does that give you any idea what would happen to the next person? Could knowledge of that first event affect the next one? And in this situation, I would assume not, that just because I grab a freshman out of a high school, that has no effect on me getting a senior next. The chance, it's not like drawing one M&M out of a bag of 10, because most schools have thousands and thousands of people. So taking one freshman out of the equation will change the probability ever so slightly, but probably not enough. So I would say knowing that somebody's a freshman has no effect on knowing if somebody else is a senior. Unless they're talking about the same person twice, maybe. I'm not sure about that. If it is the same person twice, then they can't be both of these at the same time. So then, would knowing that they're already a freshman, then there's no chance that they could be a senior. So I'm not sure if they're talking about this as one. It might be just one person the way they're wording this, the student. If that's the case, then it would be neither, because if you know somebody's already a freshman, then you can automatically know they're not a senior. And then that knowledge of that first thing helps you decide the second one, then that's not independent. So maybe that's what they mean here. No, okay, so apparently it was what I was thinking first. They should word this a little better instead of saying, oh wait, they're mutually exclusive. Oh yeah, see, I said that wrong. So mutually exclusive is when you can't be both at the same time. We can't be both of these at the same time, so it is, yes, mutually exclusive. And then I was right that the wording of this is what they meant, that it's the same person twice, so you can't, if you know the first person's a freshman, and if you're going for another person, then it would be independent, but if you're going for that same person the second time, you already know they're a freshman, so they can't be a senior. So these are not independent, because once you know the status of one, it's the same person twice, then you already know that person's status. So let me just try another one here. I was misinterpreting this. Okay, so can you be on a basketball team, and can the same person be more than 6 feet tall? Can you be both of these at the same time? Yes. In fact, a lot of basketball players are 6 feet tall. So then no, it's not mutually exclusive. Remember, it's always backwards from the way you answer it first. So can you be on the basketball team and be 6 feet tall at the same time? Yes. So then no, it's not mutually exclusive. Now, if you tell me somebody's on a basketball team, would it be completely irrelevant to determine how tall they are, or would that knowledge maybe help me decide the other one? It's not that it completely determines the other one, but just are the chances different knowing that first piece of information? If you tell me somebody plays basketball, there's definitely a higher chance, not a guarantee, but a higher chance that they're going to be 6 feet tall, because height helps in basketball. Many basketball players are 6 feet tall or more. Not all of them. Some people are less than that, but it's not like tell me that somebody is in a library and they're 6 feet tall. Just because you're in the library doesn't mean I know how tall you are. That would have no effect on it at all. But if you tell me they're on the basketball team and they're 6 feet tall, that knowledge of the first one can affect the second one. So these are not independent, and they're not mutually exclusive. This one's neither. And I did this problem, the first time I messed it up, I wasn't thinking straight, but I did this problem twice, and the answers were different. One time it was only mutually exclusive, and the next time it was neither. And if you do another one, maybe it'll be only independent. Okay, compute A and B. And okay, so see how there's an or here. Go back to the and formulas. See, A or B has an and in it, so I could use this formula right here. The formula for A or B, if they're not mutually exclusive, involves A and B. A or B is A plus B minus A and B. This is another one where we're kind of working backwards like the first problem. We're trying to find A and B. That's what we don't know. Call that X if you want. And it turns out they give you values for the other three. So A is 0.4. B is 0.2. And A or B is 0.6. Well, see, this is a case of mutually exclusive because watch what happens here. If you add 4 and 2, you get 0.6. And then you do some algebra to solve for x. I would subtract 0.6 next. So that's 0 on this side. And even though you're technically supposed to divide by -1 to make x positive, 0 divided by anything is 0. So anytime A and B equals 0, then you are mutually exclusive because that's what makes the formula drop to the shorter version. Basically, if you look at these two OR formulas, it's really the same formula. The main one that we use in college is this one here, but it turns out if you can't be both at the same time, then you are mutually exclusive. And this equals 0, and anything minus 0 is the anything. So this minus part disappears if they are mutually exclusive. So that's why the formula is so similar. It's really the same formula, except in this top one, the A and B equals 0. So if you ever solve for A and B like we did here and get 0, that's probably the point of this homework problem. If A and B ever equals 0 in an OR problem, then they're mutually exclusive because that's what it takes to be mutually exclusive. A and B are mutually exclusive because the probability of A and B is 0. And then if you subtract 0, it disappears. Okay, are they independent? They're independent if A times B equals A and B. And 0.4 times 0.2 is 0.8, and that's not 0, so they're not independent. They're not independent because A times B doesn't equal the 0 that we got for the answer to part 1. A times B is supposed to equal A and B whenever they're independent. Maybe it's because A and B does equal 0, not that it doesn't equal 0. Since A and B equals 0, that's not the same thing as 0.4 times 0.2. Oops, okay. What else was here? Or they're actually quoting the formula. See, A times B in this example does not equal A and B. It's supposed to be equal. If it equals it, then it's independent. But 0.4 times 0.2 doesn't equal the 0 answer. There we go. Okay, see, here's one of these chart problems. I like these because you can do all the types of probability without formulas, really. So we got dominant and recessive traits. Let's put that on the side. Dominant and recessive. And then the top is dominant or recessive as well. So there's two different genes. Gene 1 and gene 2. So like you have red hair, you got green eyes, things like that are genes. Genetics, the father of genetics, Gregor Mendel, he was the one that discovered all this stuff, and even though he was religious, he did, in his free time, he did a lot of math and science stuff. So some sample got 54 and 14 like this. And then we got 25 and 7 in the other column. So notice there's no totals here, so then you should total these up. 54 plus 25 is 79. 14 plus 27 is 21. And this literally adds up to 100 for the grand total. So every answer will have 100 in the denominator except for one, actually. Out of the 5 types of probability, basic or singles, complements, ors, ands, all four of those are always over the grand total no matter what. The one kind that's not is conditional. Okay, so then I've got 54 plus 14 is 68. 25 plus 7 is 32. Notice that 68 plus 32 is also 100. But don't put 200 in the bottom right. Okay, what is the probability that a randomly sampled individual in a randomly sampled individual, gene 1 is recessive? Gene 1 is recessive. That's a single basic probability. You're just going across the bottom row only. They're reviewing this even though we did this in the other one. So gene 1 is recessive. There's a 21 out of 100 chance of that. 21 out of 100. This is good over total, just the definition of probability. Good over total. And I think they want decimals, so 21 divided by 100 is nice because you get 0.21 exactly. Okay, what's the probability that gene 2 is recessive? Okay, same question, just going from gene 2. So now we're going this way. Gene 2 is recessive. So that's 32 out of 100, or 0.32. The probability that gene 2 is recessive given, see here's this conditional, given that gene 1 is recessive. So the way you write this is gene 2 is recessive given that gene 1 is recessive, or it could be dominant, but they just put recessive both times. So this is the one time that you're not going to get 100 in the denominator. What happens in the denominator is you get one of these side totals that's red or purple. You don't get the green 100. And the one that you use is the second half of the problem. In conditional, the ones that say given, you have to go to the second half first. Even the formula, I'm not even going to use a formula here, but even if I was using a formula, it's always about the second one is what you divide by in the end. Remember the formulas had the second one in the bottom? Where did I write that? Right? No, it was on the next page. Here, see how the second one is in the bottom. The second one's in the bottom. So same thing here. The second one leads to the bottom. Where is gene 1 recessive? It's this 21 right here. And then the top is either the 14 or the 7, whatever the front part's asking about. The front part's asking about gene 2 being recessive, which is this category right here. So it's that part of that row, 7 out of 21. And 7 divided by 21 is 0.33333. It's 1/3. It's 1.3 repeating. And they want 4 decimals, so just put 0.3333. The event that gene 1 is recessive, blank, is or is not independent probably of the event that gene 2 is recessive. Okay, so the way you tell this is in conditional probability. Remember what we had right here. If the probability of gene 2 being recessive, given that gene 1 is recessive, if that equals the probability of gene 2 being recessive, then you're independent. And the reason why is, remember, independent means that that one event that you do does not affect the other one. In conditional, what is happening is the second one's already happened. Given that the second one's already happened, now what's the chance that this one will happen? And if the first one doesn't affect the second one, the answer should be the same whether I take that into account or not. Whether I include the given part or skip it entirely, I should get the same answer if they're independent. So, but we didn't get the same answers. The probability that gene 2 is recessive was part B. That was 32 out of 100. 32 out of 100 isn't exactly equal to this 7 out of 21. If you look at parts 2 and 3. Only if part 2 and part 3 had been exactly equal, then we would have said, yes, they're independent. But these are not independent. The genes are not in linkage equilibrium, I guess is another way to say that. I've never heard that before. But you just say not for both of these. So say, here's a good example of this too. What's the probability that you get in a car accident? Car accident, given that it's raining outside. Do you think that's the same as just being in a car accident on a day where it's not raining, just a random day? No, because rain and wet roads and unclear vision, you can't see as well in the rain, and you can't stop if you have to hit your brakes so easily. There's definitely a higher probability of car accidents on rainy days than non-rainy days. So if I have knowledge that it's raining, then the chance of a car accident goes up. It's not the same as it would be if I didn't have that knowledge, so that's not independent. Rain can affect car accidents, that's dependent. That's what's going on here. So if you ever want to show two things are independent, do the thing you're trying to do once by itself and once with given something. Only if those two answers are identical can you say that the first one didn't affect the second one. And like I said earlier too, most things we do in college level are not independent. We don't get the easy junior high case very often. We had one problem that was, but it doesn't happen very often actually. So if you have to guess, probably your best guess is that they're not independent. Okay, I guess this one we have to make our own chart. Or maybe there's no chart here, let's see. There's 1,073 components, 218 are defective, 2 are drawn at random and tested, okay? Yeah, this is not a chart problem. Okay, so A is the first component is effective, B is the second one is defective. So what's the probability of A alone? So what's the chance of getting a defective item or component the first time you draw? This is like my M&M example where it was 3 out of 10 at first, but then it dropped to 2 out of 9 the second time. So the first time, where's my simple calculator here? The first time you draw, there's 218, whatever this is about. Normally, defective things are not good, but good over total doesn't mean like morally good or good for you, but just whatever you're interested in. So there's 218 good cases, if you want to call it that, divided by 1073 total. This is literally good over total right here. The chance of getting one defective is just good over total. And do they still want 4 decimals? Yes. 2032. Make this 1 turn into a 2 because there's a 6 after that. 2032. Now, what's the probability that the second one's defective given that the first one was defective? There was somebody at the door here. Okay, so what's the chance the second one is defective given that the first one is defective? So you have to assume the first one worked. That I found one of those 218 defectives and I left it out. If you find a defective, you're not going to put it back in there. So sometimes we draw and put things back in, but why would you put a broken piece back in? So leave that one out, and what's going to happen is the next one is, each one of these numbers is one less. So now do 217 divided by 1072. That's like my 3 out of 10 dropping to 2 out of 9 when you took the blue M&M out of the bag. And see, it's a little bit different. So 2024. So what's a chance that both of these occur? So what's happening here is I'm going to do probability of A, and then I'm going to do probability of B given that A happened. This is the chance that they both occur. So you just take your 2 decimals and multiply them together. The first 2 parts get multiplied together. 2032 times 2024. And I'm actually using a formula here. It's the second formula right here. This is what I'm doing. A and B is A times B given A. That's when they're not independent. These are probably not independent because when I make draws, it affects the next one. Independent is when they don't affect each other. So do both of these multiplied together. 20.2032 times 0.2024, 0411. Events A and B are or are not independent. They're probably not independent. I'm going to put not right away. It is reasonable to treat or not reasonable to treat as though they were independent. It's not reasonable to treat them independent because one draw can affect the next one. I don't know if that's how they're going to word it, but the sampling done was, it was not done with replacement, it was done without replacement. And if it's done without replacement, well, actually, there is a rule about this. If you have a large enough population, remember I was saying that about the high school, if the population's large enough, then if your sample is less than 5% of the population, then it can be treated as independent, actually. So how big was the sample here? We're only taking 2 out of 1,000. So I think this is kind of an exception to the rule about is it independent or not. Technically, it's not independent, but there's an exception to this that it can be treated as, it's so close that it can be independent. It's reasonable to treat it. It's not really independent, but you can treat it as independent if your sample size is less than 5% of the population. And 2 out of 1,000 is way less than 5%. It's not even 0.2%. So that's kind of an exception to it. Okay, so see, they're not really, see, I worded this wrong. They're not really independent. They're not when you draw without replacement. But the exception is this, that it can be treated as independent if this is the true case here. So I messed up the first part of that, but because anytime you draw without replacement, it's technically not independent. Every draw affects the next one. But with such a large sample size, it can just barely change it a little bit. I guess that's the point of these, how these barely changed when you did them. So then it's considered, at least it can be treated that way. Okay, this is the same problem we've been doing, but just they got, I hate these ones with larger numbers because then it takes a while to add them up. And also, if you do a slight adding mistake, then you get everything wrong, and then you can't show that you knew what was going on in this problem. But we got bilingual and not. We got a sales associate and a customer support. So we'll just say sales and customer support. 8501. 25,101. 5570. 1889. Okay, so I'm going to add up every row and every column. 8501 plus 1889 is 10,390. 25,101 plus 5570. 30,671. Now add the 10,000 to that to get the grand total. The grand total is 41,061. Okay, now add across 8501 plus 25101. The top row is 33602. And then 1889 plus 5570 is 7459. So double check that these two add up to the same grand total, because if they don't, then you have a slight typo or some major mistake maybe. 33602 plus the 7400. See, same grand total, 41061. Okay, part one wants probability of an employee being a sales associate. Sales associate is right here. This is a single probability, so I'm going to do good over total. And assuming they want 4 decimals still. Yes, 4 decimals. So do the 10,390 divided by the 41,061. Round to 4 decimals. 2530. Singular basic probability right there. Whoops, they want me to do all the parts before I check any of them. Here's another single probability, just doing bilingual. That's this row right here. So that's this 33,000 divided by the 41,000. 33,602 divided by 41,061. 8183. Keep forgetting about that, okay? So now here comes an and. See, I like these chart problems when they have smaller numbers at least, because you can do all 5 types of probability in the same problem. You don't even really need any formulas either. So see, this is the and. It's where these two crisscross each other in the table. I circled them both already. Where do they crisscross? They're crisscrossing right here. Bilingual and sales associate. These are the people that are both of those. So it's 8501 divided by the grand total. $2070. Then do they do the ors? No. They could have done an or too, but they didn't put or. But they do have the given one. Sales associate given bilingual. You don't even need a formula for this. And this is the one time the denominator will be not the grand total. Sales associate given bilingual. Go to the second part first. I like to think of this as tunnel vision. Tunnel vision down to the second half of that, to the bilingual people. This is your whole world now. Don't even look at the rest of the chart. Out of these bilingual people, there's only 33,000 of them. How many of them are what the first thing is asking for? The first part is asking for sales associates. So that's the 8501 that's in that row. So it's 8501 only divided by the 33,000, not divided by the 41. It's the one time you don't divide by the grand total. 8501 divided by the 33,000 number, which is, I still have it right there, 33,602. 2529, but there's a 9 after that. So add 1 to the 9, but think about this 9 is a 29. Add 1 to 29 and it turns into a 30. So it's 2530. 2530. So was the answer the same when I did sales associate given bilingual? Did knowing about bilingual change the probability of the first half of this? Was the probability of sales associate alone exactly the same as when I added bilingual? It is. Look, 2530 25/30. So having this extra knowledge did not change the probability. So these are independent. It's rare to get one like this, but I think they purposely did this to show you it can happen. These are independent because the knowledge of the second event, like when it's raining outside, that affects the first event, getting in a car accident. But now the probability of being bilingual doesn't affect the probability of being a sales associate. Your chance of being a sales associate is identical to being a sales associate knowing that the person's bilingual. So in other words, bilingual people, single lingual people, people that know multiple languages, you're just as likely to be a sales associate no matter how many languages you know, or at least according to this problem. They may have just made this data up to make that happen, but... Okay, so I can tell we finished 5.3 now. 1 through 8 came from 5.3. So 9 through 15 is 5.4 because now we're doing something different here. So let me give you the magic word of this third video of this unit. I can remember the first two. So let's do the Texans this time. Houston Texans will be the third one. Okay, when ordering a certain type of computer, there are 5 choices of hard drive, then 3 choices for amount of memory, then 4 choices for video card, and 3 choices for monitor. How many ways? See, this is different than the whole rest of the chapter. Everything in the chapter to this point has been about probability, but now it's how many ways. How many ways can you do something? And the reason this is in the probability chapter is it's related to probability. Sometimes in probability questions when you're trying to do good over total, sometimes either the good and or the total can be very hard to calculate. It's not a simple thing of counting it. A perfect example of that is in if you play cards and play poker, the game of poker. What's the probability of a royal flush in poker? Now, if you don't play cards or poker, you have no idea what I'm talking about probably. I try to avoid card questions on tests because some students have never seen cards their whole life or don't know games of cards. Textbooks love to put card examples in their books because they're perfect for probability. So there turns out there's 4 royal flushes if you get ace, king, queen, jack, and 10 of each of the 4 suits. So if you're doing good over total, it's very easy to do the good. There's only 4 of them. But it's really hard to figure out how many total poker hands you can get. It's in the millions, actually. It's 2.5 million, more than 2.5 million. So that's what this section is all about, is how do I find the total or sometimes even the good if there's millions of them? You literally can't make a tree diagram or count them off. It's just way too many cases. So there's 3 what are called counting techniques in this section, 5.4. 5.4 are the counting techniques. It's ways to do these really large cases many times. Now some of our homework answers are not extremely large, but that's where this is useful, is when you get an extremely large number of cases for either the good or the total. And just like everything in the previous section, previous 2 sections actually, there's a junior high kind and then there's a harder kind after that. So the junior high kind, kids on their STAR test in junior high do this kind. The first kind is called the fundamental counting principle. Here's the kind of problem they give junior high kids on their STAR test. It'll say some kid wakes up in the morning and he's getting dressed for school, and he opens up his closet and he has to choose 1 out of 5 shirts hanging there and 1 out of 6 pairs of shorts and 1 out of 3 pairs of shoes. How many ways can he get dressed? So if you do 1 out of 5 and 1 out of 6 and 1 out of 3, you have this series of one of these over and over again. You have to do 2 or more of these, 2 or more decisions of I want one of these, and keep going if need be. They put this on the junior high STAR test because it's very easy to do. It's literally 5 times 6 times 3. 30 times 3 is 90. there would be 90 different ways he could get dressed in the morning and go to school. That's what's happening on this problem. I have to choose 1 of 5 hard drives and 1 of 3 memory cards and 1 of 4 video cards and 1 of 3 monitors. See, it doesn't say 1 of, but you can imagine that that's there. Nobody has 3 monitors or 4 video cards, so you're choosing 1 of them. So I have to choose 1 out of 5 hard drives. Then I choose 1 out of 3 memories, 1 out of 4 video cards, and 1 out of 3 monitors. Literally 5 times 3 times 4 times 3. There's 180 different computers I could have them build for me out of these choices. That could be the denominator of a probability question. So keep in mind, none of these are probability. They're not going to be fractions or decimals like we're used to for probability. It's not a good over a total. This could be a good or a total, actually, in some probability question. But it's just learning how many ways can you do something, especially when it starts getting large. Okay, quiz consists of 3 true-false questions and 2 multiple-choice questions with 3 choices each. How many different sets of answers are there? So you could, like, what if you just randomly guess one of each one? How many different ways can you do that on a test? So here's a good way to handle problems like this. There's 3 true-false questions. So I'm going to put 3 questions. True or false? You have to make a decision here, and you're making a series of decisions. And each time I get to one of these 3 questions, I have to choose one of these 2. You can't choose both. True, false, you have to pick one or the other. You got to pick one out of the 2 choices. Then you pick one of these 2. Then you pick one of these 2. It's like the getting dressed in the morning. It's just every time you have 2 choices instead of the numbers can be the same or different. And then this test, and whatever this is, they also have 2 multiple choice questions where there's 3 choices each, like A, B, and C. So it's a 5-question quiz maybe, and there's 3 true-false questions, and then there's 2 multiple choice questions that have 3 choices each. In multiple choice, you only choose one of them. See, this is the fundamental counting technique. Principle, sorry. It's a series of one of these, one of these, one of these, and on tests you assume you answer all the questions. Why wouldn't you guess on the ones you don't know? So it's literally just multiplying this. 2 times 2 times 2 times 3 times 3. It's a little different sounding than the previous problem, but it's really the same thing. 2 times 2 times 2 times 3 times 3. So if you just close your eyes and point at one of each of these 5 questions, there's literally a 1 out of 72 chance that you'll get them all right. So if somebody tries to tell you, oh, I didn't study and I don't know any of the answers and I just randomly guessed them all and I got 100 on the quiz, they're probably lying to you because a 1 out of 72 chance is a very low probability. But notice I'm not putting 1 out of 72 here. We're really dealing with the total is what's happening on these kind of problems. Okay, now we're switching away from the junior high to the college level. There's 2 other versions here, 2 other techniques, and these 2 are very similar to each other. And these are not as simple. They're not hard mathematically, but they're not quite as simple as the junior high one. One's called a permutation, and the other one's called a combination. These are done not when you choose one of these, one of these, one of these. This is where you choose R out of N. I've got N total things to pick from, and I need to choose R of them. Maybe there's a class of 30 students, and I need to pick 3 out of 30 to win a prize. That's either a permutation or a combination. So first you have to get good at recognizing, is it one of these, one of these, one of these, or is it so many out of a total? That's different. So many out of a total is a permutation or a combination. And what's the difference between these? Permutation order matters. order matters or it does not matter. Now, sometimes that's hard to tell. So another way of thinking about it is the objects or the people, whatever they are, if you treat them differently, they're treated differently. If you treat objects or people differently, then order matters and it's a permutation. If you treat people or objects the same, then it's a combination. Let's say I've got 6 kids in a family and the mom wants them to do some chores around the house. And she only has 3 jobs, so 3 of them are going to be off the hook this time. She needs to choose 3 out of 6, and one of them is going to wash the dishes, another one's going to take out the trash, and the third one's going to vacuum the floors. I'm treating these kids differently because they're getting different tasks. One gets to wash the dishes, one takes out the trash, one vacuums. Order matters because if she's going to draw them out of a hat and say, okay, Johnny, you went first, Susie, you're second, probably they want to take out the trash unless they're just germaphobes and they don't want to be near trash. Taking out the trash is the easiest job. You just take it to the end of the driveway and you're done. Probably washing the dishes is the least desirable of those tasks. So whoever goes last wouldn't want to have that job, but they're going to get stuck with it. So that's a case where you have to infer that order matters and that I'm treating the people differently. That's a permutation. But if everybody's washing dishes, I just need 3 kids out of 6 to help me wash the dishes tonight. I'm treating them all the same, then order doesn't matter. Whether you're 1, 2, or 3, you're washing the dishes. You're hoping you're 4, 5, or 6 and you don't even get picked. But if you get picked, you're being treated the same. So I think this is a good problem because I think it does both cases, or maybe not, but we want a committee of 8 people. They must choose a president, a vice president, and a secretary. So how many ways can you choose a president, a vice president, and a secretary? We need to pick 3 people here. We're picking president, vice president, and secretary. We're choosing 3 out of 8. There's 8 total people here, 3 out of 8. This is not 1 of 8 and 1 of 3. I'm picking 3 out of 8. So don't do 8 times 3 here. It's not going to work. These are different jobs. President is much different than a secretary. Try telling Donald Trump that he has to be the secretary today, not the president. He would throw a fit for that because he's got to be the most important person. So clearly a president is treated much differently than a secretary is. So this would be a permutation, and the way you do this is you write 8 permutation 3, you put a P for permutation. 8 permutation 3. Now there is a formula for this, but there's 2 easier ways to do this without a formula. 8 permutation 3, you always put the bigger number first. You can't do 3 permutation 8. If I have 3 people and I need to pick 8 of them, it's never going to happen. So they usually word it backwards and they say 3 out of 8 people are being selected, but then you put 8 permutation 3. If you have a graphing calculator already, it's easy to type this in here. Type the 8. Hit this math button here on the side right below the green button. Right arrow over to PRB where it's probability. And then NPR and NCR, they're the second and third one down. So I'm going to choose number 2, NPR, because order matters here. The objects are treated differently. And then you put a 3. See, it's not 24. It's much bigger than that. It's 336. 336. Now, what if you don't have a graphing calculator yet, or what if you're not even going to get one at all? You can still do this with a simple calculator. 8 permutation 3, the way you do it manually is you do 8 times 7 times 6. Keep decreasing by 1, but stop after you have the back amount of numbers. So remember, it was 8 permutation 3, so it tells me to start at 8, and I keep going until I have 3 numbers. 8, 7, 6, that's 3 numbers. Same answer. See, it works that way too. So the good news is you can do this with or without a graphing calculator. Now, see how they're switching to probability next? See, that's my point, is that this is related to probability. What's the probability that Charlie is president and Lena is vice president? There's only one way to do that. There's one Charlie and there's one Lena. There's one out of the total number of ways to see this happen. It's kind of like you guessing on a multiple choice test and getting them all right. So this is why we did part one first. It was hard to know the total. You couldn't count that. But by doing a counting technique, I could get the total real quickly, and then the probability often is just one out of that total. Two of the committee members are Lena and Charlie. Okay, so maybe they're counting the fact that since I'm picking three people, maybe it's two. Here's what I'm thinking. Let me try this and see if this works. Maybe there's three people getting chosen for these officer positions, and I'm working with two of them. I need to choose two out of the three. And the order matters because we're doing different jobs for them. So maybe the numerator is 6. Maybe they're counting the fact that Lena and Charlie could be also the secretary instead of just president and vice president. And if that's the case, then you're getting 6 out of 336. And I think it's at a reduced fraction, so let me try this. Math, enter, enter. So let's try 1 out of 56. Let me see if this is right first, and then I'll explain what I was doing. Yes, okay. See, that's what they're considering here. So remember, we're picking three people. We're picking three no matter what. And two of them are people we care about for whatever reason. Maybe we're rooting for these people to win. Lena and Charlie, these two are two of the three getting picked. So I have to do a 3 permutation too to figure out all the ways they could land in the officer positions. So instead of getting 1 out of 336, it was 6 out of 336. And usually they like decimals in this homework, but they asked for a reduced fraction. Write your answer as a reduced fraction. If you have a graphing calculator, it's really nice if you have an unreduced fraction. If you hit math, enter, enter, it reduces it for you, whether you make it a decimal first or leave it as a fraction. And if you don't, then it's kind of painful to reduce that fraction, unfortunately. What is the probability that either Lena or Charlie is president and the other is vice president? Okay, so this is sort of what I was doing, what I thought the previous one was. And it's definitely over 336 unless I can reduce it. But see, Charlie could be president and Lena could be vice president. That's one. But it could be the other way around too. Maybe Lena's the president and Charlie's vice president. So this is 2 out of 336. Part 3 is taking out the chance that either one of them is a secretary. Where part 2, it doesn't say that. That's why I missed this one. This one is it doesn't say it, but it's apparently considering the fact that they could be secretary. But this one says they have to be president or vice president. And then this actually reduces by 2s. So 336 divided by 2, here's how you can do it manually. 336 divided by 2 is 168. So this would reduce to 1 over 168. Okay, either Lena or Charlie is president and the other is vice president. It should be 2. 2 out of 336. Math, enter, enter, is 1 out of 168. One out of 28. Okay, that's weird. What's 336 divided by 28? They're divided by 12. Okay, that's really weird. 12. How are they getting 4 times 3? I don't know this one, actually. Let's see. Example. Okay, we got the 336. That's right. There's 2 choices for president, only 1 for vice president. Okay. See, they are still doing the 6 secretary people. Okay, I see what they're doing here. Okay. See, sometimes you have to get it wrong to see what they're doing. Here's what they're doing on these 2 parts. So in part 2, we wanted what did it say? It said Lena or Charlie are president. So you got president, you got vice president, and you got the secretary. You got to do all three of these even if you're only working with two people. So either Charlie or Lena is the president. That's this one here. Either Charlie or Lena is the president, so that's two ways to pick one of those two. Then the other one's automatically vice president. And then there's 6 other people in the club because there's 8 total people. One of these 6 other people has to be the secretary. You have to pick 3 jobs. So even though the problem seems like it's only about these 2 people, you still need that third person. This is where the 12's coming from. And I forgot the wording of part 2. What did that one say? See, this one's either Lena or Charlie is president. That's 2 possibilities. Then the other one's automatically vice president. That's 1 possibility. And then there's automatically that 6 at the end. But here, Charlie is the president and Lena is the vice president. Those are 2 definitive single units, 1 and 1. Charlie has to be president, Lena has to be vice president, and then there's still 6 people left over. And then both of these are divided by 336 and you reduce them. So that's where that came from. Okay, 9 college students have applied for an internship. 2 of them will be selected. How many ways can the 2 be selected for interviews? See, here's a case where I'm not treating these people differently. They either get interviewed or they don't. There's no difference in their job titles. At least they didn't tell me in this problem. So it doesn't matter if you're first or second. You get treated exactly the same as the other person. So I'm trying to choose 2 out of 9. I'm choosing 2 out of 9. So it's definitely not 9 times 2. But the way I'm treating the people is the same, so this is a combination. If you want to do it manually, it's 9 times 8, stop after 2 numbers. And if that's all you do, it's a permutation. But if you also divide by 2 and 1, then you get a combination. So I could do 9 times 8 divided by 2 and divided by 1. And the answer is 36 manually. Or if I use the graphing calculator, 9 math probability combination 2. There's 36 different ways to choose these 2 people to go to the interview. So the part 2 is probably going to ask for a probability like the last part 2 did. Okay, see, there's 6 of the 9 are from this one college. Okay, and then what is the probability that both of the interviewed students are from this college? Okay, so what is the probability? It's going to definitely start off over 36, whatever the part A answer is. That's always the denominator to this. 6 of the 9 students are from Middle Georgia State College. So what is the probability that both of the interviewed students are from there? So we're choosing, well, here's what you do for this. It's exactly like this last one. I have to choose 2 people, so make 2 blanks. And then I'm hoping that both of these are from that college, and there's 6 total students from that college. So there's 6 that I can pick for the first slot, and then you're not going to pick the same person twice. So then the second one's 5. So 30 out of a 36 chance that they're both going to be from this college. 30 out of 36. And both of these divide by 6, actually. 5 out of 6. That seems a little bit high. Where was the problem again? Because the chance of drawing one of them is 6 out of 9, 2/3, and then 5 out of 8, but we're not choosing all 9 of them. Reduce fraction or decimal. So let's try this first. 5 out of 6. No, okay, that doesn't seem right actually. 6 of 9 students are from Georgia. Okay, so let's treat it like the M&M problem. There's a 6 out of 9 chance to get one of the 6 people to go first. That's like trying to draw the blue M&M 3 out of 10. And then I leave that person out. So now there's a 5 out of 8 chance to get the next one. But it's a little weird that this was 36 and this is 72. 30 divided by 72. 416666, so we'll make it 4167. They are allowing me to put a decimal here. 4167. Yeah, see, that was it. So what I don't get why the 36 wasn't used though in the part 2 though. It's weird that we didn't use the 36, so okay. Well, at least I got it right, but I can't explain why the 36 is not being used. Okay, here comes an easier thing. There's in the formulas for these, I just do shortcut formulas, or not formulas, but methods. So if you're ever doing, say you do 17 permutation 5, there's actually a formula for this that goes 17 factorial, this exclamation point means factorial, over 17 minus 5 factorial. But to me, it's just easier to either type it in a calculator or do 17 times 16 times 15 times 14 times 13 and stop after you have 5 numbers. So let me show you all 3 of these. If I do 17 math probability permutation 5, the answer is 742,560. If I do 17 times 16 times 15 times 14 times 13, it's exactly the same answer. And I can even do this, 17 math probability, and they got the exclamation point right below the permutation and combination. This is read factorial. So what if I do 17 factorial divided by parenthesis 17 minus 5 parenthesis factorial? This is what the formula would have you do. Same answer. So why do the messier way when the other 2 ways are easier? But maybe they just ask you to do 8 factorial, okay? So 2 ways to do this. You can go 8 math probability factorial. There's the easier way. A factorial means you go all the way down to 1, actually. So it's literally 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. That's what a factorial actually is. See, same answer. So permutations and combinations use factorials, but a lot of the parts cancel out and you don't do it all. If you do it by the shorter method, it's a little bit easier to type in a calculator. But either one of these is 40,320. How many ways can you choose a cone? Okay, there's a certain ice cream parlor offers 17 flavors of ice cream. You want an ice cream cone with 3 scoops, all different flavors. So a certain ice cream parlor offers 17 and you're choosing 3. See, we're choosing 3 out of 17. So if order matters, I would do 17 permutation 3. And this is the total number of ways you can put the ice cream on your cone if order matters or you treat the ice cream differently. Or if you don't care about the order, then you do 17 combination 3. If you're like, I'm going to eat them all anyway, what difference does it make what order they're in? Then you could treat that as a combination. How many ways? See, that's different than probability. Probability is where you have to get the good over the total, but how many ways is this a permutation or a combination? How many ways can you choose a cone if it matters which flavor is on top? In the middle and the bottom. In other words, which one does order matter? Order matters is a permutation. So there's 4,080 different ways to make the ice cream cone if you consider the order important on which one's on top, which one's on bottom. Because maybe you're probably gonna eat the top one first, so maybe you want like your favorite flavor first in your mouth, or maybe you want your favorite flavor last in your mouth. So order could matter to somebody. But give an ice cream cone to a little kid, they don't care. They're going to devour it, whatever order it's in. So what if you can choose a cone in the flavor order the flavors doesn't matter? That's a combination. That's the 680 number. So this is a good problem because it has the difference between a permutation and a combination. And the ones with probability get harder because then you got to worry about good over total. But the ones that are just how many ways, these are easier to do. How many different license plates? Okay, this is another thing you can do. License plates, a certain state has 5 digits from 0 to 9 followed by 3 letters. Replicates are allowed. How many different license plates? This is kind of like the multiple choice one. So if you're doing a license plate, or you can do passwords, passwords work exactly like this too. So every time you want to put a number, you put a blank for that. We got a license plate with 5 numbers according to the problem and 3 letters. In Texas, it's actually 3 letters and 4 numbers is how the Texas license plates are right now. So if there's no restrictions, and sometimes they do put restrictions, if there's no restrictions, then every time you see a number, you put 10, because there's actually 10 single-digit numbers, 0 through 9. You can use 0 as a number. And then every time you see a letter, you put 26. What this is kind of like the fundamental counting principle too, the junior high problem, except they wouldn't do this in junior high. It's like you have a series of decisions to make, and I got to choose one of the 10 numbers for my first number, then choose 1 of 10, then choose 1 of 10, then 1 of 10, then 1 of 10, then 1 of 26, 1 of 26, and 1 of 26. So it's literally 10 times 10, 10 for a third time, 10 for a fourth time, 10 for a fifth time, and then 3 26s multiplied together. So this is 1.7 billion license plates are possible. 1,757,600,000. That's a lot of license plates. How many license plates have the letters TIM in that order? Okay, so see, that means the last 3, you have to put T here, you have to put I here, and you have to put M there. There's only one way to do each of those. So instead of getting to choose 1 of 26 letters, I only have a choice of 1 letter. I have to put the T there. So the ones aren't going to matter. It's literally 10 times 10 times 10 5 times, which is actually a 1 with 5 zeros on the end of it. It's 100,000, a 1 with 5 zeros. One, two, you got 4 there. There's 5. 1, 2, 3, 4, 5, yeah, 100,000. If your name is Tim, what is the probability that your name is on the license plate? So write your answer as a fraction or decimal, 7 decimal places, okay? So yeah, if your name's Tim, there's only one way to do that, the way we did it, and it has a 1 out of 100,000 chance of happening. This is like buying a lottery ticket. If you buy one lottery ticket, you have a 1 in however many possibilities there are ways to win the lottery. Okay, if your name is Tim, I'm trying to think if there's another way your name could be on there. I don't think so. Fraction or decimal? 1, 2, 3, 4, 5 zeros. Huh. Where'd that come from? 17,576. If your name is Tim. Okay, so what would happen if your name is Tim? You would have to hope to get 1 out of 26 here. Yep, I'm stumped on this one too. Your name is Kemp. Okay, the total license plates. Okay, that's what they're doing. So this 100,000 is the number of ways Tim can be spelled, but the grand total is this 1.7 billion number. So you're actually doing 100,000 divided by the 1.7 billion number. Because the 100,000 is not the total number of ways, that's just the number of ways you can spell Tim. So that's the good cases, and this is the total, so this is the probability here. Now see how there's an e negative 5 here? That means times 10 to the negative 5th. So you got to move the decimal over 5 times. And it takes 1 to get past the 5, and then you'll have 4 zeros after that. This would be hard to write as a fraction, unless maybe they don't want to reduce fraction. So they would take a decimal here, but I could do a reduced fraction too, or an unreduced fraction probably as well. But so if I have 100,000 divided by 1,757,600. Math, enter, does it reduce it? No, it still makes it a decimal. So apparently you can do a reduced fraction because that's what they're saying the answer is. But see how this, I got 5.6 e negative 5. If I do their answer, it should have the same decimal version. See, 5.6 e negative 5. And what that really is 0.000056 8, 9, 5, 7, and so on. You just move the decimal over 5 times and it creates 4 zeros. Because they did say I could put a decimal to 7 decimal places. So when you do this problem, you could put 0.000056 and do 7 decimals. Don't worry about the reduced fraction because they allow decimals here. So again, sometimes you just have to get these wrong to see what they're doing, and I was thinking of it from the wrong point of view. So this is actually the good cases, and this is the total. So part 3, you're just doing good divided by total, literally. Okay, so we've reached the end of video for sections 5.3 and 5.4. Where's my Alex account? Here it is, 5.3 and 5.4. We're finished with that one now. So we've done 3 assignments since test 1. We did 3.3, 4.1, and 4.2 in one video, 5.1 and 5.2 in a second one. This is the third video, 5.3 and 5.4. There'll be a fourth video that has 6.1, 6.2, 6.3 together, and then of course there'll be a review video as well. So that's it for video 3 out of 5 of Unit 2.